Hi, everyone. Welcome to the Code Center's Data Science Tools in Action series. So before we begin, I do want to introduce the Code Center a little bit at the Virginia Tech. So our mission here is to develop and advance and also disseminate state-of-the-art data science tools that extract actionable real-world insights across the disciplines, especially in the realm of causal machine learning. And that's one of the things that we are particularly interested in developing and also working with other disciplines as well. And so we really take this interdisciplinary team-driven approach seriously at the Code Center. We work with economists, statisticians, computer scientists, and also many of the domain expertise to address complex societal challenges. So this series is designed to make the modern data analytics tools accessible across all disciplines, really showcasing how researchers and practitioners they can harness advanced tools and methods to solve pressing problems in agriculture, public policy, environment, finance, and beyond. And so this is also part of our data science for the public program, a flagship experiential learning program at Virginia Tech, where some of the brightest undergrad students across the country, they were selected to participate in an intensive summer program to learn and use data science tools to address issues of significance. So that's the reason why in our classroom here, we also have 13 very bright undergrad students here in the attending this series. I also want to mention that we also have a agri-food finance program that lots of our fellows actually very interested in learning forecasting and also applying forecasting to their work as well. And so when they mentioned this topic to me, Rami actually is the name immediately came across my mind. And so, well, I have already talked to Rami almost 2 years ago, I think. And as I wanted to invite him to give a talk. And one of the reasons is because Rami is really a very significant and active data scientist in this community, contributing to many different areas and packages and books. And so I want to very give you guys a very brief introduction to Rami Krispin. And he is a senior manager of data science and engineering at Apple, where he leads the data science and engineering team within Apple Finance, Service, and Infrastructure. So his team focuses on advanced statistical and machine learning models to support Apple leadership in making data-driven decisions. So Rami's technical focus includes time series analysis, forecasting, and he's really passionate about open source and working with data and putting model into production. He has authored a couple of very useful books, and I also subscribe to his newsletters on LinkedIn. And I think I probably heard quite a few of Rami's talks as well in the past. And I can say that I really learned a lot, and that's something that I would like to share with all of our students here as well, and also our faculty members here. And so I'm really thrilled to have today introduce Rami to be one of our speakers. Please join me in welcoming Rami.
Thank you for the intro, and thank you everyone for coming. I'm excited to talk about, always excited to talk about time series. So if you are in the right place if you want to learn about time series. Let me start by sharing my slides, and we can kick it off. And maybe I will put on the chat the repo for the materials for today's talk. And share. Let's do. Okay. Let me go to full screen, and hopefully you will see. Are you seeing my full screen or presenter mode?
Yes.
Full screen. Okay, cool. All right, so today we're going to talk about analyzing time series at scale with cluster analysis methods in R. Yeah, I've been already been introduced. So as mentioned, I'm a senior manager at Apple. I'm not representing today anything related to my work. I have to say it on every talk. And I'm very passionate about the time series and MLOps. Usually I share a lot about those two topics. I have a newsletter where I share weekly updates about different learning resources and open source for data science. And you can find me on the LinkedIn on this QR code. So with that, let's jump to the agenda. So we're going to start with a problem statement, describe what is the challenge in forecasting. We're going to talk a little bit about forecasting at scale. So it might be misleading. We're not going to do today much of forecasting, but more focus on the pre-step for forecasting about feature engineering. And then we're going to dive into feature-based time series analysis and show a demo. All the materials for this talk are available on this link. I just noticed that I didn't update or push the README. I use a template, so I need to update the README, but the rest, the slides, anything related to this talk is there. So maybe, I know if we can have a poll here, but maybe on the chat, how many people familiar with R, have experience with time series analysis and cluster analysis? A quick vote. Let's see if I can access the chat. Feel free to type on the chat. See thumbs up. We have a Python user. So anything I'm saying today is relevant to Python, right? You can implement in Python. Okay, so I feel like that most people so far familiar with something with time series or R. All right. And I'm trying to go from the full mode back to the slides. And my slides are stuck, just so give me a second. Okay. So we start with some definition. Time series is a vector of data of points measured over time. So it's a sequential data of observation that are two-dimension observation and time. Regular time series data is a time series that the measurement is equally spaced. So it could be hourly time series, monthly, quarterly, and so on. And irregular time series is a time series data that's not measured equally. So it could be that it's a random sampling over time. And forecast is a prediction of observation in the future with the time dimension. So that's the difference between prediction and forecast. So a forecast is a special case of prediction. And we're going to focus today in regular time series data. Generally, anytime that I'm referring to time series, I'm referring to regular time series data. Irregular time series is a complete different topic, and I think that most of the modelings when referring to time series are typically referring to regular time series data. So that's the scope for today. And let's start with the problem statement. And if I need to define the problem statement in 2 words, is scaling limitation. So to understand the scaling limitation, we need to look at the traditional forecasting approach. It typically will start with some business objective. For example, this time series represent the natural gas, and let's say that we want to do capacity planning, and we want to forecast the future demand for natural gas. So we need the data. And we'll start by analyzing the time series, do some descriptive analysis, explore correlation, seasonality, and so on. And then we set the modeling. We will train some models. We might use different modeling approach like backtesting, conduct experimentation with different modelings, evaluate the performance. We'll use the feedback from the evaluation to tune if needed, and then we generate the forecast. So this is a process. It's a very manual process. And so what if you have 2 time series to forecast? So you just do the same, just twice. And then what if you have 200 series to forecast? And this is where it becomes painful. And today, I think I started to do forecasting 10 years ago, where you usually had to forecast, you have 5 series, you have 10 series, but as the compute improve and the storage and ability to capture time series improved over time, I think most people today in industry are forecasting when they need to forecast, they forecasting dozens or hundreds or thousands time series. And this is where the challenge of how to identify the right modeling, how to identify the right features, and that's like it's a real challenge. So forecasting at scale, if I need to define what is forecasting at scale, is when the level of effort of adding additional time series is non-linear with marginal decay. So as you add more time series, you don't need to repeat the same process, and it's becoming less effort to forecast more. And it depends on modeling approaches. So it could be that for specific time series, we will use one methodology, and we have other time series, maybe different frequency. We'll use different modelings approach. And it very infrastructure dependency, right? So as you scale, you want to train more at scale, you need more compute power, and then it comes with the trade-off of potential drop in accuracy. And the reason is the level of effort of extracting the patterns, it might be smooth as you scale. So the amount of love and caring that you can dedicate for each time series to model each component is decaying, and therefore you end up that at scale, there is a trade-off with the level of accuracy. So let's look at the process of forecasting. You start with the raw data, could be hundreds of time series, and then you will generate features. So feature engineering could include, let's say that you have holidays if you're doing sales. So you want to model increment in sales during the holiday season, or promotions, price changes, and so on. There is the traditional features such as trend, seasonality, outlier, and so on. And then you will have a modeling framework, which you will run the experimentation, score the models, and then generate a forecast. And The feature engineering is what we're going to focus today, understand the features. And the models training and model scoring, typically in industry, we use backtesting, which backtesting in a nutshell is the time series equivalent to machine learning cross-validation. So it's a very common method to train and test forecasting models at scale. So this is a kind of like a explanation of how you conduct the backtesting. I stole it from, there is a great blog from Uber Engineering a few years ago, where they are describing how they are conducting forecasting at Uber. And you can imagine Uber, the scale is huge. And essentially, you are splitting your data into multiple training and testing partitions, where you train each time the models that you are testing on the training sets, and then evaluate the model's performance on the testing partitions. And the idea here is that you want to measure the models on the testing partition where the model didn't see it, it's only using the training. And the advantage of using multiple partition is that you want to see if the model is consistent over time. And that's a very important, which may give you indication about the potential error of the model in the future. Now, there are some caveats about backtesting. If the main assumptions that your data is not going to change, like the structure is not going to dramatically change in the future, and the testing partitions represent the future. So for example, if you were training your models just before the COVID, and then COVID started, a lot of time series changed dramatically, and what the model saw on the training and testing was not relevant for the future. So that's a big assumption. And the other method or approach for forecasting at scales is horse racing. And horse racing, as it sounds, we are running competition between different modeling approach. And the idea is that you are taking your back testing, and on each training and testing partition, you are applying multiple models. You score them on the testing partition, and then you evaluate their performance over time, and you have diversity of models. And if you are measuring by error, you probably will select the models that perform best on the testing partitions on average. And again, when you are trying to scale, it's very important not to rely just on one model, because the distribution of each series may vary, and what works for one series may not work well for other series. And this is how you can, if you have diversity of models, it helps you to scale your forecast. And essentially, backtesting plus horse racing, it's a nice name for AutoML. The concept is the same. You are trying many models, evaluate them, and select the one that perform best. So today we will focus on the feature engineering, and the main challenge on the feature engineering is how to identify the right features for the modeling approach. And or how to identify the models and how to identify the right features to use. And this is where feature-based time series analysis comes into play, and it's based on a great paper from Professor Rami Hyndman. If you're not familiar with Professor Rami Hyndman, is one of the leading people on forecasting. Is from Australia, and is for many years he was leading the forecasting development in R. So he came with this idea, or at least that's the first time I encountered with this idea. And it's when I saw it on a lecture, it's really, I feel like it's mind-blowing. And the idea is taking your multiple time series and collapse them into features, conduct cluster analysis, and identify the cluster. And then once you have cluster, you can identify similarity and for each cluster. And based on this, you can build for each cluster specific set of models. So for this analysis, we're going to use the following three approaches. So first, cluster analysis is the task of grouping observation based on similarity and similar characteristics. For this, we will use principal components analysis, or PCA, which is a method for dimension reduction, very common in unsupervised learning, which enable you to collapse if you have multiple columns, features, to collapse it into 2 or 3 dimensions. And K-means clustering is a method to identify cluster based on vector quantization, which enables us to identify K clusters. And I will just mention that I have less experience with unsupervised learning, but it's very simple, and we won't go deep to the principal component and clustering. We just demonstrate how to use it. And the nice thing that I discovered while the first time I tried to reproduce this paper is that R has those models on base R. So you don't need any external libraries to reproduce it, which is really nice. So what is feature-based time series analysis? So think about it as when you have many time series, you take each time series, you calculate features. So feature could be you calculate trend, seasonality, correlation, linearity, and so on, and collapse each time series into a single row, where the columns represent the values of the feature. So if you can see here, this table, there are 6 rows. In each row represent a time series, and the values are the corresponding values of the features. And then we apply 2 things. One is dimension reduction, that we can look at the data in 2 or 3 dimensions. And we calculate based on those feature table, either we are visualizing the features or we are using clusters. And by combining the cluster in a 3 dimension, we can start to see groups. And based on those groups, we can identify what are the common patterns of each group. So for example, here we're looking at the 4 clusters, and we are looking at each box plot represent, or each one of those box plot represent a feature. So on the top left, there is the trend, and on the right side is the linearity, and you can see on the bottom right is the correlation of leg 1. And essentially, you can see, for example, that cluster 1 has a unique trend feature with respect to the other clusters. So maybe we can identify what type of trends features we can use for cluster 1. And likewise, cluster 2 has a similar, complete different trend values. Likewise, correlation. You can see that the correlation of leg 1 is varying between the clusters. And that's kind of like give you a sense about how to approach on each cluster. You can do the process of fully tune and train on one time series in the cluster, and then try to scale it to the rest of the cluster and see if it's working. And maybe you may need to do a couple of trial and error until you get to a point that you feel comfortable, and then scaling it up. So with that, we'll jump to a demo, and I will pause for a second, see if there are any questions before I will jump to the demo.
So Rami, when you use the entropy in the previous slide,
Yes, that's a, you are referring to the feature entropy?
yeah. So you're looking at the distribution entirely?
Yes. As far as I understand this feature, it's looking at distribution and calculate the entropy score
Mhm.
and derive it from this. And maybe it's worth to see if I just for before we'll start, because you know what, I will find it. So there
Yeah,
is,
I'm just
I will show the library that I'm using, which is TS features. And let's see. So let me zoom in a little bit. So this is a great library that by Prof Hyndman and his students, which really make those features creation seamless. Let's see list of features. So you can see there is a huge amount of features that you can create. All of them are related to time series. And so, for example, you see here, this is the entropy, right? So it's there is a one sentence for each feature about how to create it, and um, there is the correlation. There, where is the ACF?
okay.
Yeah, so this is the library that I'm using to create the features.
Mhm.
Very trying to find.
Yeah, because what I'm thinking is because entropy is capturing the entire distribution. So in a way that many of the features is already captured by the entropy measure.
Yes,
So
yeah, and then again, like that, there is a trade-off when you are, throwing tons of features about the method that they are using, how to filter and identify the one that actually describe best. So there might be a trade-off when using like simple methods to more advanced, that doing better job on filtering. Like for sure, there is some duplications in the features. So when you're throwing all of those, there are some overlapping between some.
okay,
Okay.
thanks.
So let me create the font a little bit bigger. And you can see my VS Code, right? Okay.
Yes.
All right. So maybe I give just the explanation about this repo. So I'm using VS Code to run R, and I'm using it inside the containerized environment. So I have here the dev container extension, which just enable me to point to a container and run my code inside the container. So I created a special container for this workshop. So if you are cloning it and you have Docker run on your machine, you are just opening the side over here and do rebuild container or open inside the container. But if you don't want to run it in a container and you are using positron, which is a clone of VS Code, you should be able to run it. You just need to install the required libraries, and the list of libraries that I'm using for this demo over here. So it's very common libraries, dplyr, ggplot, shiny, bsly, plotly, EI, API, I'm using to pull the data from the API and so on. And TS features is the one that I just showed. So if you want to reproduce it, here is the information about the libraries, and you can generally take the install. There is should be here install packages, and this will install the libraries. The only thing that might mess your using this JSON file, it might mess your environment. So that's why I like to run it inside the container, and it's isolate. So let's do this. Let's start by talking about the data. And there are, in this repo, to reproduce the data, there is the two notebooks. One is the data refresh, which we are pulling the data. And the data that we're going to use today is demand for natural gas in the US. And this includes about 314 series. There are 5 categories, and it's monthly. So each category, you will have data for the 50 states in the US, and you will have for the overall US. And the categories are represent, for example, commercial demand by commercial entities, or demand for natural gas for cars, and so on. And so let's just open this. I already rendered it, and just see the data. So to get the data, we're going to use the EI API, which is a great resource for time series data. This is part of the US Energy Information Administration. It's part of the Bureau of Statistics, which is just focusing on US energy data. And they are providing API, it's free. You just need to go and register, get a API key, and then you can pull data from the API. It contains data on variety of energy fields, such as electricity, natural gas, petroleum, and so on. We're going to focus today on natural gas. And once you have the API, you can use the EI API library to pull the data. And to pull the data, we will be, besides the EI API, we will use dplyr to reformat the data. We're going to plot the data with plotly. We're going to do some validation with point blank, and we going to present the data with React table library. And for the Python users, everything that I'm using here more or less is also available in Python. So first thing, we're going to set the API key. I'm not going to the details of pulling the data. It's if you want, you can go after, but I'm starting by pulling the metadata for the gas, and then I'm extracting the details, the identifier of those series, and then I'm running the lapply functions on each series code and pull the series. So eventually I'm getting this table, which contain the area name, which represent the states, the type of process, for example, residential consumption, and information and the value. So that's what we care. We have the timestamp and the value, and that's what creates the time series. Now, as you can see, we have the time series is coming. The area is a little bit all over, so we're going to relabel it and generate a clean abbreviation for the labels and run some validation. I'm going fast because I want to go to the actual analysis. Once we finish the validation, you can see there are some missing values, and we're going to clean those missing values. Reformat, we create a nice reformat and unify the states name and code, and then merge it back and save the data. So this is example for commercial consumption by the 50 states. And you can see there is a lot of time series. It's very hard to see all of them because they are all over. But let's say we want to see only Alaska. It's a monthly time series, nice seasonality, and so on. So the data is going to be saved in the data folder. And once the data is there, we can start generate the features. So I will open the features. I wonder if I can go full screen. No. So now this is the fun stuff. So once we load the data, we will remove the missing values. We will transfer it into a time series object. We're using the Tsable library. So now it's in a long format where we have a monthly time series, and we have keys. Keys, the combination of the area name and the process. So it could be Alabama and VCS, probably vehicle consumption, and so on. And then the value and the index. And the next thing is we're going to generate the features. So I'm going to use the TS features library that I just showed before. And I'm going to loop on each time series and generate a bunch of features. There is a little bit of cleaning, and again, I don't want to spend time on the how to generate it. It's fairly simple loop over the time series and generate the feature and reformatting. But at the end, this is the table that we are getting. And you can see that you're going to have, for each time series, we're going to collapse each time series to a single row. So this is Alabama vehicle consumption. And then we generate a feature score for each type of feature. So the trend, it gets some value. There is a feature for spike, linearity, curvature, and so on. And we have about 25 features. Once we have the features, the next step is to run PCA. Now, the order doesn't matter. We can run k-means and then PCA, or the opposite around, it's independent. But I started with PCA, so the principal component. And R as a built-in function to run PCA, the PR comp. One of the things that we're going to do is to scale and center the values that the PCA will be easier to generate the PCA when you are scaling the data and centering it around the 0. So one thing to know about PCA, that it's collapsing the data into PCA elements. And each element will have some information about, contain some information about the variance of the data. And it's the first PCA will have the highest number of or the most significant variation about the data, and the last will be the lower. So here we are generating 25 because the data is 25. We have a dimension of 25 columns, and we generate 25 PCA. The idea is that the first 1, 2, or 3 will contain as much as information about the variation, that they can essentially explain better the data in 3 dimensions. So what you see here is that the first PCA expand the variation of 40% of the data. And the second one is 16%, and the third one is 10%. And if we take the first 3, we are getting close to 70% of the variation in the data can be explained by the 3 PCA. So again, this is something that you can maybe improve if using better features. And it's like identify what are the right features, and it's a process. But I think for now, we will use we take the 67 or close to 70 and use this for the analysis. So we're going to bend back to the features, the first 3 PCA, and you can see now we have the PCA over here. The next step is to run a k-mean algorithm that we want to identify the cluster. And when you're running cluster analysis, there is always the question how many clusters we want to generate. So what I did, I just created a loop over from 1 to, I limited to 15 clusters. And the only parameters that we're going to use for this algorithm, the k-means algorithm, is the end start. So the idea is that it's using 20, you define how many point of random start to start the search, and then it's converged to the number of clusters, or it's converged to the center of the cluster. We define the number of clusters. So those are the 2 parameters, and we're going to loop over the number of clusters. So for example, we'll start with 1 cluster, and we define the number of clusters by this variable I, and then it will always be defined as 25 or whatever you define here as the random point to start to search for the center. By the end of this process, we'll get 25 clusters, so 15 clusters, different type of clusters. And what we want to do is to look at the within cluster sum of squares, which is the very common method to identify to choose the number of cluster. And this is called the hockey stick plot. And generally the rule of thumb is that whenever you have the kink of the hockey stick, like maybe somewhere around here, it's the optimal number of cluster to use. Obviously, there is more than one method to identify the number of cluster. This is just a very simplistic way to demonstrate how to look at the number of cluster and how to make a decision. So now we are combining all together, and you can see that we have the PCA, and we have for cluster 1. Cluster 1 obviously is everything is under the same cluster, it's just finding the center. And cluster 2 is labeling each series to either cluster 1 or 2. and so on. So cluster 5, you will have 5 clusters, and each series will get a label of what cluster it belongs to. And once we finish to prepare the features, we save it, and now we can go to see the results. Any questions so far?
I think I'm good. So Rami, when you looking at the case like this previous one, how often do you encounter the plot that actually does not have a very clear inflection point?
That's a good question. I would say that usually you may want to use more than one method to cross-checking, and sometimes also beyond the checks, I did it like 15 cluster, but I just did it for the demonstration, and I probably won't go based on the number of time series behavior beyond 5 or 6. So I think it's a combination of how much you know your data, along with how much you trust the statistical method that you are doing to test. I hope this is answered. I don't think there is the thing is with the unsupervised learning,
Yeah,
unlike supervised learning that you can measure your error and say, I'm far away by the root mean square error. Here, there is no way to really say, yes, this is my error, I'm right or not.
that's right. Thanks.
No problem. And let's see, it will let me to open it. Okay. So I created this simple dashboard that just to show the data and then to go over the results. So first thing is you can see we have all the time series or the stats level. By default, it show the US and deliver to customers. And you can see there are different types of series. So if you look at the US level, you can see there is all those different categories. And if let's say that we go to the state level, you can see that each state might have a different behavior. So it can be easily, you can see it's become a mess. And that's like the issue of like identify the features when you are trying to scale it. And then this is the result. So let's break it down. This is the PCA. Now we're looking at 2 dimension. And essentially each point represent a time series. So for example, if I click on this, this is natural gas, and I probably missed here something is didn't render well, but should be the category. And this is from Iowa state. Okay, so you can see this is one time series, and if I go over here, this is from Hawaii, and so on. So each point here represents a time series. And the color represent the variable. So remember we had 25 dimensions. Now area name doesn't really mean anything. We don't really see anything. So let's maybe replace it to something more meaningful. So for example, if you look at the trend, now we can start to see some patterns. And this is going between 0 to 1, which I believe 1 is high trend and 0 is no trend. And if I click on this, you can see that if you fit a linear trend, you will get a line going up. And if I go over here, where it's close to 0, you can see it's fairly, the trend here is flat. So that's now, you can start to see patterns. And if you want, you can take it to 3 dimensions and start to look at it like this, right? So you can see now based on the colors, right? I have here a nice group. I have here another group. And in between, I have a different group. So we're still not using the we're just looking at the features. We do not explore yet the cluster. I can look for the spike. See, that's fairly, all the time series are fairly the same, but then you see here, there is one, and you can see it's also enable us to find, nice outliers. And here there are some spiky time series. So for example, in real life, you can think about automate it whenever you get this score I to calculate some standard deviation and apply some features to remove those outliers impact. Likewise, we can look at linearity. Again, you can see there is different grouping. Here there is one type of linearity, and if you go to those one, you can see there is no linearity in those ones, so and so on. Correlation is another nice one, right? You can see over here there is I correlation for leg one, so it's ACF1 autocorrelation function, and the reason is that you can see the nice patterns that each observation is fairly close to the previous observation. That's why you will see that those type of series will have high correlation as opposed to those one, right? It's a flat and so on. Now let's move to the cluster. So looking at the cluster, this is where it's also becoming more interesting. You can see that you can choose the number of clusters. So let's just go for 5 clusters. And now you can start to see the groups. And this is where you can start to think, okay, now I can actually look at groups and identify what makes each group special. So I just plot here 4 features, but you can think about doing it for more features and start to think about what is unique. So if I'm looking at this time series, obviously you can see that it's very strong seasonality, monthly seasonality. More or less the trend is either low or flat. Compare, let's say, to this group, which is more like a step function. And this group is a little bit more oscillate. There is more trend component, and the oscillation here is probably like seasonality, but it's not as pronounced compared to this seasonality. So again, like the time series from here, we can think about different type of features and models and with respect to this one. And you can go and, let's say, if you want really to go and see like 10 groups and start to think maybe, to go in the smaller groups, you can use this, increase the number of clusters. It might be more confusing than giving information. So you need to think about when you want to stop. But, if you want to do deeper segmentation for a specific group, so you can really look, this was the same cluster before, now it's 2 different clusters. What is so special about this that it's different from this? And maybe here, there is a little bit linearity trend, and that doesn't exist here. And again, this is the challenge with unsupervised learning, that there is no right or wrong, or there's no like clear answer, and there is more experimentation that you need to do. But the next steps from here would be define like the number of clusters. Let's say that you want to be modest and choose 5 clusters. I will take specific series from here, try to fit modeling based on the characteristics, and then try to scale it to the whole clusters, measure the error, and see if the distribution of error is across the cluster is reasonable, or we need to do additional tuning with more series. And so instead of training on analyze on 300 series or more, you can split the job into 5 different groups, identify each group, its uniqueness, build the features for that group, and then scale it to the whole time series. And I will pause here and see if there are any questions.
Great. So Rami, but after you classify them into groups, then will you run? So what type of model will you run then in this case?
So you're referring to the forecasting models that I would run.
Mm-hmm.
Yes.
Are you gonna talk about that in a minute?
No, so I didn't want to go to forecasting because we have 1 hour.
Yeah.
But generally, for me to do the forecasting is straightforward. For me, you can really apply the back testing. I think is the key is to understand the characteristic, and based on this, build the features and apply it and scale, if it makes sense.
Daria has a question. Go ahead.
Yes, I wanted to ask. So this is machine learning. I'm curious, Rami, would you make an attempt to interpret these clusters, mapping it to kind of like an intuition of your non-technical stakeholders who I would imagine think they know their clusters pretty well, and then you're trying to get their buy-in, and then you need to like kind of describe what the machine learning discovered as a clusters and why they should be treated differently. Will be there that step, or you omit it and just prove that machine learning part works well because like the error is small? What will be your strategy around that?
I think it really depends on your relationship with your stakeholders and their expectation. Typically, when I work with my stakeholders, I try to expand them, and also they have a better knowledge about the behavior of the time series, so their knowledge is very valuable. And when you encounter them in the process, I think it can contribute to the features that you are generating, but also gain their trust in your output. So I usually try to have my stakeholders to be part of the process and have interaction. Just there is the side of building the trust, and then there is the business knowledge that they have better than I do that can translate into features, and it's very important. I hope this is answer your question.
Yes, it does. I would, if I paraphrased it, I would say you want them to help you with feature engineering in a way, but to win their feedback, you need to translate your work into their language, right? So
Yeah.
you would make this effort. Yeah, makes sense.
Yeah.
Thank you.
Thanks.
I think I have a similar question or concern to Daria, where the models seem to be statistically identified, but the economics is lost on that. For example, I have no idea how to truly connect those principal components to economic variables or anything like that from the data that we could actually say to somebody that, hey, let's say this is exactly what the first 3 principal components truly are. So I think that's the part that is a little bit troubling is not the right word, but a little bit uneasy for me.
I think principal component to expand to non-technical stuff is one of most challenging. I agree.
Exactly. Yep.
I think, trying to expand with visualization, and also you don't necessarily need just the principal components. Or, yes, you need to expand the dimension reduction, but I agree that sometimes I understand well what principal component does, but I have a hard time if I need now to explain you as a technical audience the math or the eigenvalue and all those things and go to the math behind of it, I probably will get lost. So this is, I think, where using visualization could be very helpful. And I think, again, like it's building a trust. At the end of the day, if I would use something like XGBoost to forecast, it's also sort of black box to communicate to my stakeholders. But if you are building this trust and walking them on your steps, I think that, again, it depends on working with different stakeholders, and each group might have a different preference and requirements. Some stakeholders don't really care about it, just want the results, and some they want to be able to explain to their stakeholders and so on. So I'm not sure if I answered your question, but I agree that it's a challenge. And I think being a data scientist, sometimes beyond your skills of data scientist, you need to be also sort of, I would say, psychological, and identify your stakeholders, their needs, and what make them happy, or how to explain them, or how to sell it, like this. And that's like the soft skill of data science.
That's
Sure.
right.
Yeah, I agree.
I actually like the way that you present the features of each group and to categorize that. I think it maybe one way to do it is also to have a, is it Rami disconnected?
No, I'm here, but I'm not sure why my video, I think my
Yeah, okay.
internet is
No,
low.
because you stop at a very nice pose.
Please
Yeah,
if
no,
you can.
I actually really like the graph that you had. It is very telling of some of the features of each group. And I think maybe one of the things that be a little bit more exploratory is try to link those groups back to those features that you have and see which one actually is most important ones, explaining those group membership. And then the second step would be after you identify the important variables that can explain the group membership, and then focus on those most important variables and to see what kind of pattern you can actually discern, and that would help us to interpret the group membership a little bit further.
Yeah.
Yeah, so I really like that one. For example, the trend one is really standing out, right? For some of the groups, you actually have a very significant trend. Probably some of them are a positive trend, some of them are negative trend, and some of them have no trend. Probably those are explaining the why you're actually finding those group, and then adding the group features would become much more important later.
Yeah, and I think when you communicate to your stakeholders, they should probably have some sense about what's happening on the back end, like what are the drivers, and then this is where you back it with the features.
Yeah. So how, I think how often do you find that? So do you also compare in some cases that, so the idea of to do this at scale is because you reduce the dimension in some sense, right? And when you're reducing the dimension, one of the inevitable limitation of that is you imposing the homogeneity in the modeling for the group that you have. So do you sacrificing some of the heterogeneity there? You sacrifice some of the more specific features. How often do you find that limitation actually will get in the way of generating a more accurate forecasts?
You're probably going to, so really depends on how the variation of your series, and at the end of the day, when you're doing cluster, it's capture some of the variation, right? It's not 100%.
Yeah.
And you may miss some of the variation. So if you try to generalize it, and this is where the trade-off with the accuracy, what you can do is once you deploy those models into production is to monitor and then identify where the models doesn't perform, and maybe do some fine tuning ad hoc to specific time series that it does not perform well. And the thing usually in scale, you may have some time series that have more level of significance to you than others. So you will also prioritize those one and spend more time on those. And then there might be others that, how to put it, there is a trade-off between spending the time on those one and might not be really impactful. So that there is always a trade-off between time, computational power, and the level of details. You cannot, I think we cannot win it all. And when you acknowledge that you cannot win it all, you probably can do a better scaling. Monitoring will help you to identify where you're really failing and should really go and address.
Yeah. All right. Do we have any other questions from the audience?